Since the late 1920s, astronomers have believed that the fabric of space stretches over time and that galaxies are carried along with it. Einstein's relativity equations were instrumental in the development of the secular Big Bang story of origins. But new data from the James Webb Space Telescope continue to tell us a different story. How is it reshaping secular theories and suggesting a new creation-based cosmology? Coming up on today's edition of Origins, Webb Telescope Discoveries Part 2 with Dr. Jason Lisle. Hello, welcome to Origins. I'm your host, Ray Heiple. We have a great show for you. Today's guest, Dr. Jason Lisle, is a creationist who researches issues pertaining to science and the Christian faith. He earned his PhD in astrophysics at the University of Colorado in Boulder. Dr. Lisle has worked at Answers in Genesis, the Institute for Creation Research, and in 2017 he founded the Biblical Science Institute. As a popular speaker and author, Jason presents a rational defense of a literal Genesis, showing how science confirms the history recorded in the Bible. Welcome to the program, Jason.
Thanks.
We're going to be looking at Webb Telescope Discoveries Part 2. What are we going to be talking about?
Well, I want to share with you today some original research that I've done using data from the James Webb Space Telescope. And it's exciting stuff because it challenges the secular Big Bang model. In fact, it pretty well refutes it and opens pathways to brand new creation research.
Well, I thought it was fascinating in Part 1 how we began to look at the Webb telescope and compared it to the Hubble telescope. And I think that really helped our audience to understand why we had this other one and what are the advantages. And I'm hoping that we're going to build on that and you can bring even more of this interesting subject to our audience.
Yes, so the Webb Space Telescope, really kind of the successor to Hubble, it can look out deeper into space than Hubble can because it's able to reach wavelengths that have been redshifted. They've been shifted toward the into the deep infrared portion of the spectrum, which means it can see galaxies that are so far away that their light has been completely shifted down into these wavelengths. And that's why it's able to peer deeper into space than the Hubble Space Telescope. And this led me to publish an article, and you can find this. It's actually published in the Answers Research Journal. So for those who say, well, creationists, they don't publish in peer-reviewed journals. Well, here it is. It is there. And it's called Sizes of Galaxies in James Webb Space Telescope Data Suggest a New Cosmology. That is the understanding of how the universe, its structure, and how it unfolds. And I need to give some historical background for this to make sense. Back in the 1920s, the physics that Einstein discovered was relatively new. I think he'd published his general relativity in 1915, and it explains how gravity bends the fabric of space. It explains how light moves and so on, and how objects move in a curved space-time. And people were beginning to play with this, and four physicists in experimenting with Einstein's physics tried applying it to the entire universe. And they found that it was possible for the entire universe, for the fabric of space, it was possible that the fabric of space could be either expanding or contracting. And they independently published their results. The four scientists, their names were Friedman, Lemaitre, Robertson, and Walker. And the metric, which is the sort of mathematical structure of an expanding space, is named after them, the Friedman, Lemaitre, Robertson, Walker metric. Okay. And that's a mouthful, so sometimes we shorten it to just the last two, the Robertson-Walker metric. But in any case, this describes the fabric of space as either being expanded or contracted. Now, also in the 1920s, Edwin Hubble was an astronomer who was doing some measurements on galaxies. He was measuring their distances using Cepheid variable stars, which are these stars that pulsate, and there's mathematical ways to compute the distance to them. And then he was also measuring the velocities of these galaxies using their Doppler shift. And he found that most galaxies are moving away from us And the farther away they are, the faster they're moving away from us. It's almost a linear relationship. The farther, the faster. And he published that in 1929, what's now called the Hubble law, after Edwin Hubble. And these four physicists, especially Lemaitre said, you know what, that makes sense, because if the fabric of space is expanding, then sure enough, the farther away a galaxy is, the faster it'd be moving away. And you can picture this like if you imagine painting little dots on a balloon, and then you blow up the balloon, right? Two dots that are close to each other, they'll move apart a little bit as the balloon expands. Two dots that are already far apart will move away much faster, won't they, because of the expansion of the balloon. And so this was accepted as the explanation for the Hubble law. The reason that galaxies are more redshifted the farther they are away is because the entire universe is being stretched out or expanded like a balloon. Now, not everyone embraced that model, but most physicists did. There was one guy named Zwicky who proposed an alternative. He said, well, maybe the reason that the farther away a galaxy is, the more redshifted it is not because it's moving away, but because light just kind of loses energy as it travels. And so the farther away light is, the more redshifted it is because it loses energy. And that's called the tired light model. Now, it predicted a blurring effect that we do not see, and so most people rejected the tired light model, especially today now that we have these crystal clear images of these distant galaxies. But nonetheless, the Robertson-Walker metric that describes the expansion of the fabric of space, with galaxies just kind of going along for the ride, that's become the standard explanation for the Hubble law. And I must admit, I thought it was the right explanation for most of my life. I was taught that in school, and in grad school I learned how to do these calculations and figure that out. But some of the data we're seeing from the James Webb Space Telescope have challenged that model. And so that's what I want to talk about today. The idea that the fabric of space may not be expanding at all. Galaxies might just be moving through space. And if that's the case, then it really challenges the Big Bang model of the universe.
Could you take us up to the board and show us a little more?
Yeah, sure. Now, on the one hand, you might think that there would be no differences between galaxies that are merely moving through space versus space itself expanding and carrying those galaxies along with it. But it turns out there are some differences in what you would expect. In an ordinary space that's not expanding, the kind that's more intuitive to us, the farther away something is, the smaller it looks. This is just perspective. And this works for galaxies too. Galaxies that are relatively nearby, like the Andromeda Galaxy, it looks quite large. And in fact, it's about as big as the full moon in a telescope. Galaxies that are further away, they get smaller and smaller. If their true size is the same, they appear smaller. This is just perspective. And if a galaxy is twice as far away, it will look half as big. That's pretty easy to compute. And that's the way the galaxies would be if space is not expanding. But it turns out if space is expanding, the light gets stretched, and that creates a kind of a magnification effect. A lot of people don't even know how a magnifying glass works. They know that somehow the light gets bent, but it causes the image behind it to look larger than it would. Well, it turns out if space is being stretched, it creates the same effect. Objects that are farther away will look bigger because the light's been traveling through space longer. And it turns out at a certain distance, well, for small distances, perspective dominates and galaxies will look smaller and smaller. But at a certain distance, this magnification effect is larger than the decreasing size due to perspective. So if space is expanding, galaxies will look smaller and smaller, and then they'll start to look bigger and bigger. And it turns out it's not very far out in space. It's at a redshift of about 1.6, which is where the light's been stretched 1.6 times. At that distance, galaxies should look smallest. But beyond that distance, this magnification effect is greater than the decreasing size due to perspective, and galaxies will start to look bigger again. And I remember learning how to compute this effect when I was in graduate school and being able to calculate how big a galaxy should look at a given distance. And I was expecting to see that effect in the James Webb Space Telescope data. I was expecting, because it can see galaxies that are way beyond a redshift of 1.6, it'll go out to a redshift of 20. And at that distance, the galaxies should look bigger than the galaxies in front of them. I was expecting to see that, but I didn't see that. If you take a look at this image of distant galaxies from the James Webb Space Telescope, the farther away galaxies are, the smaller they are. You don't see this magnification effect. Now, you do see a little bit of magnification in certain galaxies, like these ones right here. You see these galaxies that look like they've been stretched. That's due to the fact that the Webb telescope is pointed at a galaxy cluster. These white galaxies are foreground galaxies, and these reddish ones are in the background. And the light from the distant galaxies has to go past the gravity of all the stars in the nearby galaxies to get to us, and that does act like a magnifying glass and distorts the image a little bit. But that's due to this cluster. Out here, where you're far away from the cluster, the smaller galaxies, the ones that are really far away, look tiny. They don't look bigger. And so that made me think, why are we not seeing this magnification effect? And then it occurred to me that magnification effect only happens if the fabric of space is stretching. So I thought, what if the fabric of space is not being stretched? And again, that may sound like there's no difference, but there is, because you don't get the magnification effect. See, we know from the Hubble law that Edwin Hubble discovered back in the 1920s, basically 1929 is when he published it, that the farther away galaxies are, the faster they're moving. So it's like that. The space between galaxies is increasing. But we don't necessarily know the cause. Most people assume it's because the fabric of space is stretching and the galaxies just kind of go along for the ride. But if that's true, these distant galaxies should look much bigger than galaxies that are nearer. And we don't see that. On the other hand, if the fabric of space is just kind of static and the galaxies are simply moving through space, you wouldn't see that magnification effect. And so what I'm suggesting is that the standard model, the Robertson-Walker metric, which describes the expansion of space, I'm suggesting that is wrong. That space is not expanding, carrying the galaxies along with it, because that would create magnification effect, which we do not see. What I'm suggesting, I'm going to call it the Doppler model. I'm going to suggest that the reason galaxies are redshifted is not because the light's been stretched in an expanding space, but simply because the galaxies are moving through space and their light has been Doppler shifted. And so what I'm suggesting is basically this. Galaxies move through a non-expanding fabric of space. So the universe is expanding, the galaxies are moving away from each other, but the fabric of space doesn't expand with it. And that would not create this magnification effect. Now that's all fine and well, but does it match the data? That's what I wanted to know. Well, I remember how to do these calculations from grad school. And so what I did was I took a typical size galaxy, 4.5 kiloparsecs, and said, let's push that out at various distances and see how big it would appear if the standard model is right, which is the Robertson-Walker metric, if space is expanding, versus if space is not expanding and light is simply, or the galaxies are simply moving through space. And then I also compared the tired light model, this idea that Zwicky came up with, that light just kind of loses energy. And you get 3 different predictions indicated by these 3 lines. If the standard model is right, upon which the Big Bang is based, the Big Bang requires that galaxies should look smallest at a distance of a redshift of 1.6, which is right about there. And then they will get bigger and bigger and bigger after that. Until you get out to a redshift of 20, they should be quite large. If, on the other hand, space is not expanding, the galaxies are simply moving through it, then this is how big they should look. And it should be smaller at all distances, but you can see they continue to get smaller. There's no magnification effect if the Doppler model's right. If the tired light model is correct, then this green line will be the size of a galaxy at various distances. Okay? So, and now it turns out I didn't have to go through and measure these sizes. Other astronomers have done it. They've measured the sizes, the angular size, how big a galaxy looks, of these distant galaxies. And so I simply took their data, which they made publicly available, and plotted it on this chart. And now galaxies come in a range of sizes, and so we would expect quite a bit of scatter. And these are the authors of the various papers from which I obtained their data. And you can see that some galaxies are bigger, some are smaller, but the average size is kind of close to the yellow line, isn't it? It's pretty close. There's a few galaxies that are up here, but there are none that are above it, not once you get out to here. But remember, this line indicates the size of an average galaxy. And so what I did is I took the average size, or actually the median size of the galaxies in each bin, and said, which line will they line up with? And that'll indicate the correct model. And here's the answer. Wow. They line up beautifully with the Doppler model. Isn't that interesting?
That is.
So this is the average size, or median size, of a galaxy in a redshift bin. And the vertical bars indicate sort of the range. That's a 1 sigma standard deviation for those that are into the math of this. And you can see that the average size of a galaxy lines up almost perfectly with the Doppler model. It doesn't line up well with the standard model. In fact, the standard model is not even within one standard deviation of the data. So pretty amazing. And you might say, well, the tired light model still has a chance, right? Because it's pretty close, but the best answer is the Doppler model.
Jason, this is fascinating, but I have to stop you right there. We need to take a break. Stay with us. We'll be right back after these messages.
We hope you're enjoying Origins TV. It all started at Cornerstone Television in Pittsburgh, Pennsylvania. We've been producing new episodes for over 37 years now. We praise God for the success of the program and are excited to introduce you to Origins and to us. If you're interested in watching more episodes of Origins, you can find them on our YouTube page. Simply go to YouTube and search Cornerstone Television Network. Click the like and subscribe buttons, then you'll find the best episodes of Origins in our playlist. You can also visit our website at ctvn.org/origins. One more way you can stay connected with us is to subscribe to our free monthly Hope Today newsletter, which you can do from our website. And if you have any questions, call us here at Cornerstone Television at 888-665-4483. We'd love to connect with you. Thank you for watching.
Welcome back to Origins. We're talking to Dr. Jason Lisle, who's been sharing about Webb Telescope Discoveries Part 2. So Jason, we left off looking at this model that does not conform. The data does not conform to what the standard model says. What do those who adhere to that model, how do they answer that? Do they have an explanation that would allow them to show why there's an anomaly here?
Well, yes, there is an explanation for this, and I have made an assumption. And they could attack that assumption, and that's exactly what they've done. I have assumed, when I plotted these curves, these are the curves for a 4.5 kiloparsec galaxy. I've assumed, because that is typical, that's sort of an average size galaxy nearby, I've assumed that that's also the average size for distant galaxies. Now, the way the secularists could get around this, they could say, no, the standard model's right, the red curve's correct, but galaxies are actually smaller as you go out. And so the reason that we don't see this magnification effect is we actually do see it. They are magnified. It's just they're, in fact, really tiny.
Okay.
And that works. And in fact, most of them have just assumed that. They've just assumed that these galaxies, but they'd have to be 10 times smaller than galaxies that are nearby. And yet we already know they have the same mass. The mass is estimated by the amount of light, more stars, more light, more mass. And so we know they're similar in mass to nearby galaxies. So they're assuming that they're actually 10 times smaller, which would make them 1,000 times denser because they're 10 times smaller in each dimension. It's not just that they're 10 times smaller at, say, a redshift of 20. If you look at that curve, they're just exactly as much smaller as they should be to make the standard model look wrong and the Doppler model look right. I mean, each and every point, I mean, they would have to grow in exactly the right way to make my model look right and the standard model look wrong if the reverse were in fact true.
That's
so
convenient.
Yeah, so it's like that's a pretty big coincidence to think that they grow in just the right way as to cancel out any evidence of an expanding space. So I would argue that on the basis of Occam's razor, that the simplest explanation is usually the best. The simplest explanation is that these galaxies are in fact the same size as nearby galaxies. They have the same range. It's just that we're not seeing a magnification effect because it's not there.
So space is not expanding.
Space is not expanding.
The galaxies are moving through space.
The galaxies are moving through space. Exactly, yeah.
So, and how does that support a biblical model versus a Big Bang model?
Well, for one, it pretty much eliminates the idea of a Big Bang. Now, you might think, well, if the galaxies are moving away from each other, even if space is static, if the galaxies are moving away from each other, you run the movie backwards, shouldn't they all come to one point? And the answer is no, because galaxies have a bit of sideways motion too. I'll have to make an animation for this at some point. But basically, if you run the movie backwards, the galaxies will miss because they're not all moving exactly away from one point. They're moving generally away from one direction. But if you run it backwards, they'll miss each other and go past and just go out into space. In fact, some galaxies like Andromeda are blue shifted right now. You run the movie backwards, they get further away. So you can't have a Big Bang unless space itself contracts, and that forces all the galaxies to go back to a point. But we've seen here that space isn't expanding. The evidence is consistent with the galaxies simply moving through a non-expanding space, and that eliminates a Big Bang.
Okay, and these galaxies that are moving through, they're already mature again. They're already fully formed. They have their full mass, as far as we can see.
Yes, so one of the implications of this is that distant galaxies, no matter how far you go out, are about the same as nearby galaxies. We already knew, and secularists would already concede, they're similar in terms of mass, similar in terms of morphology, spirals, ellipticals, and so on, and metallicity. They already have the heavy elements. So they would already agree with us on those essentials. And now we would see, if space is not expanding, they're also similar in terms of size.
And when we're talking size, we're talking like from one end of the galaxy to the other.
Yes.
And they're saying that everything's compressed, right? Yes. 10 times smaller size, so everything's closer together. All those stars and all those solar systems and all those planets. I mean, just in my mind, that's going to cause a problem. What about all that gravity that's so much closer together, and how's that interacting with that?
Yeah, well, I mean, there is a lot of space between stars and galaxies, so I don't know that it would disrupt solar systems to make them 10 times closer. But nonetheless, it's just, why would they magically expand and at just the right rate to make the red line look wrong and the yellow line look right? So I think that's special pleading. And then there's one other line of evidence too, that the Doppler model is right. And let me show you this. It's not just the angular sizes of galaxies that are affected by the model, but also their brightness, how bright they should appear. And it turns out that in the standard model, if you assume the standard model and you assume that galaxies are about the same brightness there as here, then the red line would be correct. That shows you how bright galaxies are in terms of their magnitude. Magnitude's kind of weird because it's reversed. The more negative it is, the brighter the galaxy is. But the black line is the Doppler model. And we would expect that the brightest galaxies, and the reason I use the brightest galaxies come in a wide range of brightnesses. Some are very faint, some are very bright. But I figure at a given distance, a galaxy that's sort of the brightest in that bin ought to be sort of typical. So I took the brightest galaxy in each bin, and the black line should be, if the Doppler's model is right, there should be a downward trend. Basically, galaxies that are nearby should look a little brighter, and galaxies that are farther away should look a little fainter, already compensating for the fact that they're further away. Okay, and then the blue line is the best fit to the actual data points. The data points are indicated in the little squares there. The blue line is the actual best square or least squares fit, and you can see it's downward sloping. What that indicates is that indeed the distant galaxies, their intrinsic brightness is a little bit fainter than it should be if the standard model is correct. And so it fits approximately the slope of the Doppler model. This is an independent confirmation of the Doppler model. Not only does it predict the correct sizes of these galaxies, their angular sizes, how big they look, but also their intrinsic brightness is about the same as nearby galaxies if the Doppler model is right.
So you have that same motion, that same relative angular motion versus the standard, which is not at all going in that direction, and the data here is showing that.
Right. So this is a way of showing that the data basically fit the predictions of the Doppler model, not only in terms of size, but in terms of the brightness of these galaxies.
Has there been an answer to this yet?
I haven't seen an answer to this one yet.
Okay.
Yeah.
You'll have to stay tuned. We'll have to stay tuned.
Yes. So if you're keeping track, basically the angular sizes of distant galaxies are consistent with their redshifts being caused entirely by the Doppler effect, motion through space, which causes the wavelengths to be stretched out a little bit. It's not due to the Robertson-Walker metric, the stretching of space itself. The galaxies merely glide through a non-expanding space. The sizes are consistent with that. And then we've seen the brightness of these distant galaxies is likewise consistent with the Doppler model, not with this Robertson-Walker metric. And again, I was a believer in the Robertson-Walker metric until these latest results. And the nice thing about this is it refutes the Big Bang. It suggests that no substantial galaxy evolution has occurred. We already know that, and secularists would agree, that distant galaxies are about as massive as nearby galaxies. Well, they have the same mass, same morphology, and they also have heavy elements in them, just like nearby galaxies. So they're already the same on those three. And now we've seen, if you use the Doppler model, they're also the same in terms of size, and they're the same in terms of brightness. And what that indicates is that galaxies do not evolve over billions of years. There's no evidence of galaxy evolution.
We're seeing nothing that's a little bit beforehand in the galaxy life. It's always the same.
Right. this idea that the secularists were expecting to see how galaxies change over time by looking back in time, looking into space, we're not seeing it. There's no galaxy
evolution. They're always the same age, as it were. They're always the same, form and so forth. That's really fascinating.
It really is. It really is. And then of course, the Big Bang cannot occur without an expanding metric, because there's no way to get all the galaxies back to a point. If they're just drifting through space, they'll miss each other if you run the movie backwards in time. So this really eliminates a Big Bang. And it's also consistent with what I call the ask model, which is a model I've proposed to explain how God got the light from those distant galaxies to Earth within the biblical time scale. Some people have asked, was this a different model? Well, it's explaining two different things. The two models go well together. They dovetail. So I'm an advocate of both the ask model and the Doppler model. They're explaining two different aspects of creation.
This is really fascinating because, creationists have been okay, at least they've been able to work with the expanding space model, but Big Bang cosmologists can't. I mean, if they lose the expansion, they lose their theory, whereas the creationists could work with both, but
Sure.
What you're finding with the Doppler model, that's even more in line with creation since it rules out a Big Bang.
It is, yes. And again, I was a creationist and believed that the universe was expanding. I just didn't think it started from zero.
Yeah.
So there's nothing anti-biblical about an expanding metric. It's just the data don't bear it out. The data are consistent with a static fabric of space and galaxies merely moving through it.
Well, thanks for being with us today, Jason.
My pleasure.
And thank you for watching. On today's program, we considered the standard model of space expansion that is a necessary component to the dominant theory of Big Bang cosmology with concrete data gathered from the Webb Telescope. The results did not at all conform to a Big Bang model, but instead showed consistency to the biblical account of creation. It just goes to show you that we know what the Bible says is true because the proof is all around you. If you enjoy Origins, we sure could use your help to keep this creation television program on the air. Your support, both prayerfully and financially, make a big impact. So let's work together to reveal how awesome our Creator truly is. And we'll see you next time right here on Origins.
Thank you for watching this edition of Origins. For a DVD of this series, you can order online or send a $12 donation to cover shipping and handling, and write to Origins Program number 2508, Cornerstone Network, Wall, Pennsylvania 15148.
This presentation was made possible by the faithful prayers and financial support of you, our Cornerstone family.